Welcome back. We're going to continue our discussion of graphs and digraphs by focusing on some applications to PageRank. In order to discuss PageRank, we're also going to go over Markov chains and Markov matrices. A Markov chain is a sequence of possible events in which the probability of each event in the sequence depends only on the previous event. For example, let's consider a very simple Markov chain, which involves eating food. If I eat pasta on a day, then I will only eat pizza or only fries on the next day, each of those with equal probability. So I can make my choice for the next day just by flipping a coin, assuming that I eat pizza on the previous day. If I eat fries on a day, then I'll only eat fries or I'll only eat pizza on the next day, each of those with equal probability. Again, I can use a coin to determine it. But if I eat pizza on a day, then I will only eat fries or I'll only eat pasta on the next day. The fries I'll eat with probability 2/3. The pasta I'll eat with probability 1/3. For these probabilities, we can use dice to determine what we'll eat on the next day. Note that for all of these probabilities, there's no dependence on the previous days. Only today is what affects tomorrow. And these rules that I've written, they hold for every day. So every next day's food only depends on the previous day's food. Let's look at an example. Suppose that today I will eat pasta with probability 1/2, pizza with probability 1/4, and fries with probability 1/4. So what is the probability that I will eat fries tomorrow? In order to calculate this probability, we can break it down into a sum of products. The first product is going to be the probability of pasta today times the probability of fries tomorrow if I eat pasta today. The second product will be the probability of fries today times the probability of fries tomorrow if I eat fries today. The third product will be the probability of pizza today times the probability of fries tomorrow if I eat pizza today. When I add these three products together, I get 1/2 times 1/2 plus 1/4 times 1/2 plus 1/4 times 2/3, which gives us 1/4 plus 1/8 plus 1/6. And this simplifies to 13/24. Now let's look at a more interesting example, the web surfer. Remember that the links on the internet, from pages to other pages, they form a digraph and will exclude any links from a website to itself. So we can think of surfing the web like taking a random walk on a directed graph. One way that we can do the random walk is we can take the current website that we are at. We can count the number of distinct links at our current website, and we'll let that number be L. We will choose a random link on the page uniformly with probability 1/L, and we will go to that link. If the current page has no links, then we'll just stay at the current page with probability 1. Note that the word uniformly means that all possibilities have the same probability. So in this case, when we're looking at websites, we're saying that all distinct links on the current site have the same probability of being chosen to click in our model. Instead of doing just a random walk, we'll do what is called a lazy random walk. Whatever the current website that we're at, we'll stay there with probability 1/2. And instead of going to each of the distinct links with probability 1/L, we'll go to each of those links uniformly at random with probability 1/2L. Again, L is the number of distinct links on the page. If the page has no links, again, we'll stay at the current page with probability 1. This changes what happens a bit, because now, even if we're at a current web page that has a bunch of links, it's possible to stay at that web page for a very long time, which wasn't possible with the ordinary random walk. Now that we've looked at Markov chains a little bit, we're going to discuss Markov matrices, which will vastly simplify some of our computations involving Markov chains. Consider an n by n matrix. The rows and columns correspond to n states, S1, S2, up to Sn. For example, with the food scenario that we considered earlier, we have n equals 3, and the 3 states are pasta, fries, and pizza. For the other example we considered, with the surfer on the internet, the states are the websites on the internet, and n is the number of websites, so it is large. Now, for the Markov matrix, the definition is that the entry ij is the probability of transitioning from state Si to state Sj. Note that, by definition, the entries in all rows add to 1 and are non-negative. For example, this Markov matrix right here is the Markov matrix for the food Markov chain that we discussed earlier. That first row is the row for if I ate pasta today. The 1-1 entry is the probability that I will eat pasta tomorrow if I ate pasta today, which is just 0, as we can see in the 4th bullet. The 1-2 entry is the probability that I will eat fries tomorrow if I eat pasta today. We can see that that one is 1/2. Let's look at another entry. The 2-3 entry. This one should be the probability that I eat pizza tomorrow if I eat fries today. And we can see from the 5th bullet that that should be 1/2, and that's exactly what it is in the matrix. Let's look at one more. How about the 3-2 entry? The 3-2 entry should be the probability that I eat fries tomorrow if I eat pizza today. According to the last bullet, that should be 2/3, which is exactly what we see in the Markov matrix. Now we can use that Markov matrix to do some calculations in a much simpler way than we did before. Suppose that the probability that I have pasta, fries, or pizza tonight is 1/2, 1/4, or 1/4, respectively. In order to find the probability that I will have pasta, fries, or pizza tomorrow night, I can do a simple matrix multiplication now. I can take 1/2, 1/4, 1/4 as a row vector on the left, and I can multiply it by the Markov matrix that we just calculated on the previous slide. When we do this matrix multiplication, we get the row vector 1/12, 13/24, and 3/8, where 1/12 is the probability that I have pasta tomorrow night. 13/24, as we calculated earlier, is the probability of fries tomorrow night. and 3/8 is the probability of pizza tomorrow night. More generally, we can do this process for a Markov matrix M with n states, S1, S2 up to Sn. If we have a row vector V, which equals P1, P2 up to Pn, so that the P1, P2 up to Pn are all non-negative and sum to 1, then we can take the product Vm. Vm, like V, is going to be a row vector. And the ith entry of Vm is going to be the dot product of V with the ith column of M. Recall that, by definition, the ith column of M is the vector whose jth entry is the probability of the next state being Si, assuming that the current state is Sj. So the dot product of V with the ith column of M is given by the sum j equals 1 to n of the probability of currently being in the state Sj times the probability that our next state is Si, given that our current state is Sj. That sum, when we add those probabilities together, we get the probability that our next state is Si. So the ith entry of Vm is just the probability that our next state is Si. Again, assuming that the ith entry of V is the probability of being in state Si in the current state. Just like with V, we can note that the entries of Vm are non-negative and they sum to 1. Now let's consider an example where we have states that are websites. Our websites are S1, S2 up to Sn, and we will let L of Si denote the number of distinct links from Si to other websites. So L of Si is the out degree of Si. We will first form a matrix P for the random walk without including the laziness part yet. The ij entry of this matrix P will be given by 1 over L of Si if Si has a link to Sj. If Si has no link to Sj, but Si has a link to some site, the ij entry of P is 0. If Si has no links, the ii entry is 1, and the ij entry is 0 for all j not equal to I. To get the lazy random walk matrix W, that is just obtained by taking W equals the identity matrix plus P divided by 2. Here's another problem for you. If M is an n by n Markov matrix with states S1, S2 up to Sn, and K is a positive integer, what probability is given by the value in the ij entry of M to the K? Now, let's discuss PageRank. PageRank gives us a vector whose entries are scores for the websites on the internet. We'll suppose that we have some search engine. The search engine uses spiders to crawl the internet. These spiders are just programs that find new websites. Suppose that there are n websites that have been crawled by the search engine spiders, and we're only surfing the internet on websites that the spiders have found. So we won't go to any websites that the spiders have not found yet. Suppose further that V is a row vector that gives the probabilities that we are currently at each website. If we use the lazy surfer model, the vector VW gives the probabilities that we will be at each website in the next time step, where again W equals the identity matrix plus P over 2. PageRank is a bit different than the lazy surfer model because it adds in a probability that sometimes we'll go to a website that is not linked from the current page. In order to achieve this, PageRank uses a seed vector S, which has the same length as V. For example, we can take S to be the vector where all the entries are equal to 1 over n. We could also take S to be a vector where one of the entries is 1 and all the other entries are 0. That first example of S would be a uniform vector. The second example would be a personalized one. For example, the website that has the 1 on it could be your favorite website. Another personalized vector could be a vector that has 2 zeros and then all the other entries are 1 over n minus 2. So for example, those zeros could go on your 2 least favorite websites and all the other websites would have an equal probability. For PageRank, we'll fix some real number A in 0, 1, non-inclusive. The vector A times S plus 1 minus A times V times W will give the probabilities that we will be at each website in the next time step, assuming that V gives the probabilities that we are at each website in the current time step. We want to find a solution for P to the equation P equals AS plus 1 minus A times P times W. In other words, we're trying to find a fixed point of the function f of V equals AS plus 1 minus A times V times W. This is the same function of V that we see in the top bullet. The vector AS plus 1 minus A times V times W. And I claim that the sum in the fourth bullet gives a solution for P to the equation in the second bullet. That sum is P equals A times sum J equals 0 to infinity of 1 minus A to the J times S times W to the J. I claim that the sum converges since 1 minus A is less than 1. And if we want to find P, if we want to approximate P, we can just calculate it by finite sums. So here is another problem for you. Prove that the sum above gives a solution for P. So now that we have found P, we have a non-negative score for every website that the spiders crawl. So here's an outline of our search engine process. First step, the spiders crawl the internet by going to the links on their current page or using sitemaps. Then the search engine indexes the sites that the spiders crawl, analyzing and cataloging the content of each site. Finally, when you search some keywords on a search engine, the search engine uses its index to find the relevant sites for your keywords, and then it ranks them. How does it rank them? It can just use the P, the probability P that we calculated, with some seed S that is personalized for you or uniform. Thanks very much for watching.